Hey everyone, and welcome back to the channel. Have you ever wondered how you can get different voltages from a single battery, or how you can smoothly dim a light bulb or control the speed of a small motor? The answer often lies in a clever device called a potential divider. Think about your phone charger. It takes the high voltage from your wall socket and steps it down to the low voltage needed to charge your phone. That's a form of voltage division in action. Today, we're going to dive deep into a specific component that does this job beautifully. The rheostat will explore what it is, how it's built, and how it masterfully works as a potential divider. So, what exactly is a rheostat? The name itself gives us a clue. Rhea comes from the Greek word for current, and stat means to keep stationary or to control. So, a rheostat is essentially a device used to control the current in a circuit. It's a type of variable resistor, which means unlike a standard resistor with a fixed value, you can change its resistance. This ability to vary resistance is what makes it so incredibly useful for a wide range of applications, from controlling the brightness of a lamp to adjusting the volume on a stereo system. Let's break down how a rheostat is constructed. Imagine a cylindrical core, usually made of a ceramic material because it's a great insulator and can withstand heat. Around this core, a resistive wire, often made of a nickel-chromium alloy like nichrome, is wound. Why nichrome? Because it has high resistivity and doesn't rust easily. The two ends of this long resistive wire are connected to two fixed terminals, which we can call terminal A and terminal B. The total resistance between A and B is the maximum resistance of the rheostat. Now, here comes the magic part. There's a third terminal called the sliding contact or wiper, which we'll call C. This slider is designed to move along the length of the resistive wire. As it moves, it makes electrical contact with the wire at different points. This sliding action is what allows us to change the resistance. The slider is connected to a shaft, which you can move using a knob or a lever. So you have three terminals in total, the two fixed ends of the wire A and B, and the movable slider C. This three-terminal setup is crucial for its function as a potential divider. So how does this all work together to control a circuit? Let's consider its primary function as a variable resistor first. To use it this way, we typically connect only to terminals to our circuit, one of the fixed ends. Let's say terminal A, and the sliding contact, terminal C. The current flows into terminal A, travels through a portion of the resistive wire, and exits through the slider at C. The other fixed terminal, B, is left unconnected. Now, as you move the slider C closer to terminal A, the length of the wire the current has to travel through becomes shorter. Since resistance is proportional to the length of the wire, a shorter path means less resistance. Conversely, if you move the slider C away from A and towards B, the current has to travel through a longer section of the wire, which increases the resistance in the circuit. According to Ohm's law V equals IR, if the voltage from your power source is constant, increasing the resistance will decrease the current, and decreasing the resistance will will increase the current. This is how a rheostat controls the flow of current, allowing you to, for example, dim a light bulb. More resistance means less current, and the bulb gets dimmer. Less resistance means more current, and the bulb gets brighter. But the real versatility of the rheostat shines when we use it as a potential divider, also known as a potentiometer. This is where all three terminals B and C come into play. To set this up, we connect the power source, say a 9-volt battery, across the two fixed terminals. A and B, we connect the positive terminal of the battery to A and the negative terminal to B. This establishes a voltage drop across the entire length of the resistive wire. The potential at terminal A is 9 volts, and the potential at terminal B is 0 volts. Now, the output of our circuit is taken between one of the fixed terminals, usually the ground or -1, B, and the sliding contact C. So, our output device, like a small light bulb or a voltmeter, would be connected between terminals B and C. Here's how the voltage division happens. The total voltage from the battery is dropped uniformly across the entire length of the resistive wire from A to B. The voltage at any point along the wire depends on its position. When the slider C is all the way down at terminal B, it's touching the point with 0 volts potential. So the voltage across our output between B and C is 0. Now, as you start to slide C upwards, away from B and towards A, you are tapping into points along the wire with progressively higher voltage. If you move the slider to the halfway point between A and B, you'll be tapping into a potential that is exactly half of the source voltage. In our example with a 9-volt battery, the output voltage would be 4.5 volts. And if you move the slider all the way up to terminal A, the output voltage will be the full source voltage of 9 volts. Because C is now in direct contact with A, essentially, the sliding contact divides the total potential across the resistive wire. The ratio of the resistance between the slider and the bottom terminal B to the total resistance of the wire between A and B determines the fraction of the source voltage you get as an output. So V_out equals V_ multiplied by the ratio of R_BC to R_AB. By simply moving the slider, you can continuously vary the output voltage from 0 up to the full source voltage. This principle is incredibly powerful. It's the mechanism behind volume knobs on old radios. Turning the knob moves the slider, changing the voltage supplied to the amplifier, which in turn changes the loudness of the sound. It's used in dimmable light switches to vary the voltage sent to the light fixture. In scientific labs, rheostats are used as potential dividers to provide precise variable voltages for experiments. They are also used to calibrate instruments and control the speed of motors by adjusting the voltage supplied to them. So, to recap, a rheostat is a 3-terminal variable resistor. When used with 2 terminals, it acts as a current controller. But when all three terminals are used, with the source voltage applied across the two fixed ends and the output taken from the slider, it functions as a potential divider. This allows us to tap into any fraction of the source voltage, giving us a smooth and continuous range of output voltages. It's a simple, elegant, and fundamental component that gives us precise control over electrical circuits. I hope this explanation has made the workings of a rheostat as a potential divider crystal clear. It's a concept that pops up everywhere in electronics, and understanding it is a huge step forward. If you found this video helpful, please give it a thumbs up, as it really helps the channel grow. Don't forget to subscribe and hit that notification bell so you won't miss our next deep dive into the fascinating world of electronics. If you have any questions or ideas for future videos, drop them in the comments below. Thanks for watching, and I'll see you in the next one.